Okay, I think we can start. Right, the past week or so you've been looking at the dot product, and this week or next week you'll be starting with a cross product. Now the important thing about the dot product is that the answer is always a scalar. That's why we also call it the scalar product. And this is your basic definition. Any vector A and any vector B, the magnitude of A, the magnitude of B, cos of the angle between the two. And you can also write it as AB, where AB is not a line. A is the magnitude of the vector A, and B is the magnitude of the vector B. Now A and B can be any two vectors. It can be like two forces. You want to find the angle between two forces, and it's the magnitude of the one and the magnitude of the other and the cos of the angle between the two. That is your dot product. But you can also use something like this. Let's say a position vector and a unit vector. Because these vectors can be anything. They don't have to be the same. They don't have to be, both have to be forces, or both have to be position vectors. They can be different. So, position vector AB, unit vector CD, the magnitude of the first one, the magnitude of the second one is of course 1, magnitude of a unit vector, and the cos of the angle between the two. Or they could both could be unit vectors. Or the one can be a force and the other one a unit vector. Doesn't matter. You don't have to use the same type of vector. So, okay, that's your basic definition there. And make sure that your answer is always a scalar. Don't add an I and a J and a K to the answer. Answers are scalars. It's just a number. Now, another thing about the dot product, there's another way of working out the dot product. Instead of working out this right-hand side, there's a way of working out what is A dot B. So let's say you have two vectors, A and B. And you want to find the angle between the two. Okay, now A dot B, if you write that out, then you get something like that. I plus J minus K dot minus 2I plus 5J plus K. And now you multiply the I with the I, and the J with a J, and the K with a K. And now I dot I is 1, and J dot J is 1, and K dot K is 1. But if you multiply those two, you get minus 2, and those two give you a plus 5, and those two give you a minus 1. So I dot I and J dot J and K dot K, they are all 1. And note I get scalar values. Now I, J's and K's on this side, because I dot I is 1, and J dot J is 1. So you take them in pairs, I with a I, a J with a J, and a K with a K. So I for a I, a J for a J. Okay. So that adds up to 2. 5 minus 3 is 2. So that means A dot B is 2, but A dot B is also the magnitude of A times the magnitude of B times the cosine of the angle. So now I have the left-hand side. It's easy to work out the magnitude of A. That would be 1 squared plus 1 squared plus 1 squared, square root. And that one will be 2 squared plus 5 squared plus 1 squared, square root of that. So you can work this out, and then you can get cos theta. Cos theta is then A dot B, which is 2. And this is the magnitude of A and the magnitude of B. So this square root there is that square root of that function B, 4 squared unit. Ignore the minus signs because you take -2 everything squared. That's 4. Okay, so you got that, and that gives you the angle. Okay, so that's the important thing about the dot product, and there are many applications of the dot product, but I'm not going to go into that now. Okay, this is the important thing you have to know at the moment. Now, there are two things you can do with a dot product. One is you can find the angle between two vectors, and the other thing is you can get the projection of a force on a line. So let's say I have a 70 Newton there, and I want to know what is the projection of that force on this line. Projection on this line. So if I drop a perpendicular there, what will that distance there be? What will the magnitude of that be? Now, okay, if you have the angle, then it's simple. Then it's 70 cos theta. That will be that. Now, if you don't have the angle, there's another way of doing it. And you had a little bit of that in last week's tutorial, I think about the last problem or so. The projection of a force on a line is given by the force dot the unit vector along this line. This unit vector here. So U, E, O. If you dot those two, you will also get that projection. And one can prove that. You get the same answer as in the case where you have the angle and you say 70 cos theta. So instead of working out the angle, you need to work out this. But this is not the only thing you have to work out. You also have to get that force as a vector. It's a vector dot a unit vector. So you've got to write that force as a vector. Now you know there are last week's tutorial, you had 3 methods which you could write a force as a vector. And the obvious method here will be to use those position vectors. To get that position vector and then to write the force. Let me show you here. The force itself will be 70, the magnitude, times the unit vector which runs from B to A. So don't get mixed up with these things. You did this one here in the red box. You did that last week. To write a force as a vector, you just take the magnitude and you multiply it by the unit vector which is in the same direction as the force. One can also write this as 70 times the unit vector in the direction of the force. Now note the difference between that one in the green box and this one in the red box. That is a vector dot a vector. That's a dot product. That's a scalar. This is 70 times a unit vector. This is a vector. So that's what I want to work out, but before I can work that out, I've got to get that force. The force is 70 times the unit vector, which runs along that same line as the force. So, in order to get that, your unit vector, which runs along BA, will be the position vector, which runs along BA. Position vector divided by the magnitude of the position vector. You can write the magnitude like this, or you can write it like that, the absolute value of the vector. So, you've got to get the position vector. You should know how to get the position vector, the final values, those values minus those values will give you that position vector. So eventually you get something like that. So there's your force. So that's this one over here. Now I still need the unit vector which runs from B to 0. So that's simple. Coordinates here is 0. There's your coordinates. So it's the 0 coordinates minus those coordinates will give you that unit vector. Let's just check that. 0 minus 1 is plus 1. And 0 minus 4 is minus 4. And 0 minus 5 is minus 5. The magnitude of that thing is 1 squared plus 4 squared plus 5 squared. That's 42. So there's your unit vector. Now what do I do with this unit vector? I've got to take the force dot the unit vector. So here's my force. I've got to take that dot this one. So in your final calculation, this is F dot that, work it out, simplify it, you get the magnitude of that section over there is 57,1. And of course, if you want the perpendicular value there, then you can just use Pythagoras. Because now you have the 70 and you have the 57,1, and now you can get that one over there. You don't have to work it out with a dot product or something like that. So this is the second application of a dot product. The one is to get the angle between two vectors. The other is to get the projection of a force or of any vector. But in this case, a force on a different line. So you have a force in one direction, you have a direction there. You want to get the projection of that force on this line. And you use the unit vector, unless you have the angle between the two. Then you can say 70 cos theta. And 70 cos theta will also give you this answer over here. But you've got to know this method as well. Okay, just to repeat again, or not quite repeat, but sometimes they ask you to write that projection as a vector. What is the vector here? It has that magnitude, but what is the vector? The same we did on the previous page. We had that 70, but we wrote that 70 as a vector. Of course, the magnitude of this vector will be 70. 30 squared, 60 squared, 20 squared should give you 70. Now the same over here. If I have that magnitude there, what is the vector running along that line? So they could ask you, find the projection, the magnitude of the projection, or they can ask you, write that magnitude, find the projection and write the magnitude, or write the magnitude as a vector. Write that force as a vector. So then you use the force times the unit vector. Which unit vector? The one which runs along this line. The same we did on the previous page. That force as a vector was that 70 times this unit vector. Not dot the unit vector. Dot the unit vector is going to give you this one here. So that times that unit vector, and in this case, this magnitude times the unit vector running along BO. And then you just simplify that, you get this vector. So it's that projection written as a vector. And the magnitude of this one will be 8,81 squared plus 35,2 squared plus 44,1 squared. Square root of everything should give you 57,1. Okay. So those were the two things about the dot product. Find the angle and to find the projection, and furthermore to write the projection as a vector. So always check, what are they asking? The projection, just the magnitude of a projection, or the projection as a vector? Okay, you can think for yourself, well, how are you going to get that one as a vector? Yeah, I can write this as a vector, you can write that as a vector. How are you going to write that one as a vector? That's something else. Okay, let's go on to, I've still got another page here. Just to summarize, that force there as a vector will be the magnitude of the force times the unit vector in the direction of the force. So that's the force as a vector, and this projection here will be the force dot the unit vector. Which unit vector? Along that line. Along the line of projection. So along the line A, B. So here's a F dot. There's just F times that. That gives you a vector. This will give you a scalar. Okay. Okay, enough about that. Let's move on to equilibrium. Oh, no, before equilibrium. One of the problems you have is this one. They say get the projection of this force along a certain line. Now we just saw to write the force as a projection, you've got to have this force as a vector. So how do you write this force as a vector? Well, let me give you a hint. This force as a vector, well, you have here, the components of that force will be this one and that one. Those will be two components of that force. This component here is in the y direction. So this component here is the y component of the force. Makes sense. It's parallel to the y direction. Now what about that one there? It's not parallel to the z-axis and it's not parallel to the x-axis. Now in order to get the z and the x components, you can break that one up. Let's see if I have a ruler here. No. Okay, you can break that up into, where's the x direction? The x direction is here. You can break that one up into a component there, parallel to x and parallel to z. So something like that. So that component of f, you can break up into these two components. And this component will be the x component of the force. Of course, it's parallel to the x-axis. And that one there is parallel to the z-axis. So that is your z component. So I start off with these two in blue, which is obviously components of that force. This one is parallel to y, so is the y component. That one is not parallel, but you break it further up into two components, and they are your x and z components. And once you have that, you can just fill in the angles and work out. If you have that three components, then you have the force as a vector. Of course, the force is going to be fxi plus fyj plus fc. Okay. And once you have that, then you can go to the next step where they ask what is the projection of that force on the line, I think, OA. So then you use that, which we just did a moment ago, F dot a certain unit vector. Okay, so that is that problem there. Right, let's look at the next thing. I want to talk about some of these problems and give you a few hints. This one here, okay, they give you this drawing and these forces between A and B, and they ask you what is the magnitude of that force and what's the magnitude of this force and what is that angle theta, and they say the weight of that one is the same as the weight of this one, but they don't give the weight. The weight is an unknown, if I remember correctly. Yeah. And they ask you to find the mass of each sphere, the angle theta, and the tension in the cores. Now, when you're doing a problem in equilibrium, it is always important to isolate a certain point. So you say, you take point A. You just look at point A and all the forces acting on point A. And you draw a free body diagram of A. And then you go to B. And you just look at B. Forget C and A. Just look at B. All the forces acting on B. Now the forces acting on B will be that one there, and that one there, and this weight. Forces acting on A will be this one, the force there, and the weight. You have three forces there, and you have three forces there. This force, of course, here at B, you can just as well draw it on the other side, it doesn't matter. And this force on A, you can also draw it on the other side. But okay, if we were to look at a drawing of that, okay, let's look at B. On B, as I say, you have a force there, a tension force, pulling B in that direction. You have that force, and you have the weight. So it's going to be something like this. Tension force, you have that angle there with a vertical. You have this force here, 0.02 Newton, 20 millinewton, and you have this weight. So you have two unknowns. If you have two unknowns, then you can solve it, because you can say the sum of the forces in the x direction is 0. That's your one equation. And the sum of the forces in the y direction is 0. So you have two equations, and you have two unknowns. Two equations, two unknowns, and you can solve. If you have 5 equations and you have 5 unknowns, then you can solve it. So you can solve TB and you can get this weight. Okay, so you just look at B. Those are the forces at B. Now you go to A. Now important, what you can remember here is that this weight of B is the same as the weight of A. So you already have the weight of A. But okay, A is going to be something like this now. See if I can fit that in here. So on A, you have that same force between A and B, 0.02. You have an unknown force here, TA, and you have a weight. Okay, there's also an unknown angle there. That angle there is going to be the same as the angle here with the vertical. So, this is your picture. Those are the forces. You have the weight. So again, you have two unknowns. So now you can write the sum of the forces in the x direction is 0. Sum of the forces in the y direction is 0. So, and then you can solve it. So initially you have 1, 2, 3, 4, 5 unknowns. Well, actually 4, because this one is the same as that. So you have 4 unknowns in your problem, but just by looking at B, you can solve those 2 unknowns with your equations, sum of the forces in x direction, sum of the forces in the y direction. And then you do exactly the same with B. Okay, so that should help you there. Then another quite tricky problem, if I can just get the drawing. Okay, over here. Now, number 320 and 32. 320 and number 32 are very similar. If you can do this one, you should be able to do 32 as well. Okay, what do they give us here? They say, now it's completely a different way of putting it. They say the maximum tension allowed in these wires is 600 Newton. Determine the maximum mass of the chandelier that can be supported. So they don't give me this mass. They don't give me the tensions here. They just say, what's the maximum tension? That's 600. Only thing I have is some angles here. Okay, what you do again, you start off, let's say you start at D, and you just look at D and all the forces acting on D. And you try to solve that as far as possible. And then when you finish with that, you can go to B and solve that one. And remember this force here, the force at D is the same as the force at B. At D, the force is in that direction, and at B, the force is going to be in that direction. But the magnitude of the force is exactly the same. Same at B, the force acting in that direction, pulling B in that direction, is the same as that force acting at A in that direction. Okay, so what I did was look at D. You have this force, and this weight here. So, you get the following picture. You get that force, and you have this force. Now you have three unknowns. But you only have two equations. The equations are the sum of the forces in the x direction and the sum of the forces in the y direction. So you have two equations, but you have three unknowns. So you can't solve it exactly to get a number. What you're going to get in this case is going to be something like this. Just to simplify it, let's say I have something like x plus y equals 3m. Those are my three unknowns. And I have another equation. So I have two equations, but I have three unknowns. How do you solve that? You go about it just as you would when there were two unknowns. If you solve this, if you add these two, you're going to get 4x. It's 8m. So x is 2m. So y is m. So that's the best you can do. You can get x in terms of m. And you can get y in terms of m. So when you go to this problem, you're going to get exactly the same situation. You're going to get these forces in terms of m. In fact, you're going to get something like that. FCD, that force there, is 7,18m. And that force there is 8,795m. You don't know what m is. M is one of the unknowns. But you write it like that. So that's the best you can do for point D. And now you go to point B, that point over there, and you do exactly the same. Now for point B, this force here, BD, is the same at D and at B. So that force there is the same as this force. At B, it's pulling in that direction, and at D, it's pulling in that direction. So you have that force there. Let me show it like this. That force there is the same as this force over here. And once again, you try and solve this, but you have three unknowns. Well, actually you have this one now. You have solved it in that section there, and you got FBD is 8,795m. So this is 8,795m. So you use that with this, and you solve the others, and you get those two. Now, they say the maximum force should not exceed 600. Now, where's your maximum force? You can see the maximum force is in AB. It's 12 times the mass. This one is 4.5. That's 8,7. That's 7,1. The maximum is 600. So that means this one is 600. That's the largest force. So, to repeat quickly. As I say, problem 20 and problem 32 is similar. You first look at this one. You have this force and that force, and you have the weight, mg. And then you look at that one, and you know this force is the same it's the same as the force you found here. So as I say, you have three unknowns. You set up your equations. Your equations is going to be something like this. So those are going to be f of a, b, and f of c, d, whatever. You're going to get answers in terms of m, in terms of the mass, m. I've multiplied the g in 9,81. So this is what you get. You know the maximum is 600, so you check which one is the largest. So that one is 600, so that is the one. So this one is going to be 600. Okay. Just one or two last things. Problem 29 and 33 involve a lot of mathematics. It's more mathematics than something else. This one here, number 29, and the same with that one over there. And then you have one problem with a spring. Just a last remark, something about a spring. Let's say you have a spring with a spring constant of 1,000. You attach a mass to it, 10 kilogram. The question is, what is this distance before it's in equilibrium? You attach the mass to it, it extends, and it stops somewhere over here. So, how do you solve it? Okay, what's the forces on this one here? Remember, it's now in equilibrium. The spring is extended, it's elongated, and the whole thing now is in equilibrium. Here you have equilibrium. Equilibrium. Your forces are mg, or 10g. And the other force is the force in the spring. Force in the spring, which is the spring constant times this distance s. That's all. Hooke's law. Hooke's law says the force in a spring is the spring constant times this extension or elongation. So it's in equilibrium, so that one should equal this one. So Fs equals Ks is mg. K is 1,000 and mg is 10g. And so now you can solve the distance s. What was that extension? Okay, so you always look at the point of equilibrium and you say, okay, why is it in equilibrium? Because there's a downward force, the weight, and there's an upward force, the spring force. And they should equal each other, and when they equal each other, then you can solve it from there.